In this lecture, we're going to continue our discussion of the kinematics involved with performing a single knee extension exercise. And so although we're not going to fill in this graph here on the slide, this graph is a very important reminder that when we talk about conducting a kinematic analysis, we're focusing on three variables, all of which are going to be a function of time. So we have to have an understanding of the initial position, in our example of knee extension, the position of the knee, as a function of time, will allow us to determine the angular velocity, and from which we can then determine the angular acceleration. And so this graph here presents real data sampled from a research participant performing a knee extension, a weighted knee extension task, as we illustrated previously. And these data were sampled with an electrogoniometer, so a device placed to the leg that tracked at a very high rate the angular position of the knee, so that we would be able to model and fit a smooth curve to the movement of the knee. So here we see the knee starts at a position of approximately 90 degrees. As it approaches almost 180 degrees, but full knee extension here as a function of time. So a little bit of movement at the beginning as that is modeled, a little bit of movement in the opposite direction at the end. And so to derive the next kinematic variable, which is velocity, essentially what we want to do here is envision individual points and how those points change with respect to time, is essentially calculating the instantaneous slopes. So if you imagine walking up this hill, if this were a hill, the most difficult part of the hill would be the steepest part. But we have to have a way to identify how the slope, how the steepness of the slope is changing as a function of time. So at the very beginning of the movement, we see that we have essentially at this instant, we have a zero slope. So we have a perfectly horizontal line indicating that there is instantaneously around this point zero change in position as a function of time. Therefore, the velocity will be zero. But as the leg starts to move, we start to see the slope beginning to increase. It reaches a maximum point somewhere in the middle, and then it starts to plateau, where the speed will start to slow down, and then it approaches zero again when the knee has stopped moving at terminal knee extension. So we can say that the knee extension maneuver is increasing in velocity. It's speeding up, hits a peak, and then slows down to a zero, as indicated by the slopes of each of these lines, and we can determine almost an infinite number of slopes all throughout this motion. And when we do that, we can then track the pattern in velocity as a function of time just with the one knee extension maneuver. So the maroon line here is actually a model of real data. So a third order polynomial function was used with regression analysis to develop the maroon curve. And this function has the form of theta as a function of time, where time is the independent variable that will determine the value of knee angle. And A, B, C, and D are coefficients of this equation, of this function, that are specific to each individual knee extension task within its, for even one person if they perform multiple knee extensions, or between people. So the coefficients will be specific to the individual repetition. However, the overall form of the function will be used to model that pattern. So what we see here here we have angular position from the previous slide, and here we have angular velocity derived from this pattern here. So a very effective tool used to conduct kinematic analyses is not just calculating a few values from selected points in a movement, but by examining the entire pattern of the movement. And to capture that pattern, we use functions to do that. So if we take a look at this particular angular position time function here, we see two distinctive shapes to this curve here, and the separation between the two shapes is defined by this point, and this is called the point of inflection. And from the point of inflection, what we saw in the previous slide, that this is the point at which the slope is steepest. And we know that when the slope is steepest, the derived variable, which is velocity, is going to be at its greatest value, and we see that happening right here. Now, if we take a look at these two individual shapes, the front half of this pattern here, the front half of this curve, has this sort of shape to it, so that if it continued in this pattern, angular position would continue to move up, up, and up. We call this concave up. So the concave portion of this curve is facing upward. But that's not what happens here. What we see here on the second half of this curve, we have something called the concave portion of this part is facing down. So we would call this concave down. The connection between these two is the point of inflection. So the angular position of the knee would continue to increase in this manner unless some external factor came in and caused the trajectory of this pattern to reverse into decreasing slopes. And that's what the point of inflection tells us. It provides us with an indication that from a biomechanical perspective, something is going on here. So if we continue to extend this to a full examination of all the kinematic variables, we start with angular velocity, and from angular velocity we wish to derive angular acceleration, and this is the pattern that emerges. So if we start and locate the largest value, the greatest value for angular velocity, we see it's at the apex of this curve. And then we know that at the apex of this curve, the slope is going to be horizontal or zero. And so we can automatically assume that the graph here will be zero. So the acceleration function will move through that point. And if we examine the slopes throughout the angular velocity, we see that the slope is steepest at the very beginning. And at the very beginning, we know that no acceleration values will be greater than this, and it's heading in a positive direction. So what we see here on the front half of this function, we see that the knee is experiencing positive acceleration. Remember, the knee is at a resting state, velocity is zero, and in order to get the leg to move, it has to experience a significant change in velocity, which is positive acceleration. But acceleration continues to decrease where acceleration is zero, where velocity peaks. So when the knee extension is getting faster, it's still accelerating to where it peaks, and then on the back side of this, on the second half of this, we see that velocity is starting to slow down. And that's indicative by the negative acceleration. So the negative acceleration tells us that the knee is accelerating in the opposite direction. It doesn't move in the opposite direction because it already has a significant amount of momentum generated from the positive acceleration. So the negative acceleration is necessary to counteract the positive acceleration to bring the knee to a resting state in the terminally extended position. And the resting state is defined as zero motion. So the pattern that we just observed for angular position is modeled with this function here. So this function was generated from the data collected from one research participant performing one knee extension task, where A is the first coefficient, B is the next leading coefficient, C and D are the remaining coefficients for this third order polynomial function, and the independent variable is raised to a power of 3. We have the next term raised to a power of 2, raised to a power of 1, and of course there's no independent variable. It's just a constant that rounds out this angular position function. To derive to derive velocity from position and then to derive acceleration from velocity, this is a process called differentiation, where we essentially compute slopes throughout the entire curve to generate a new function. And that new function for angular velocity is presented right here. So here we have 3 new coefficients, but we have 1 less coefficient. So the 92.2 constant is eliminated when we differentiate this entire function into a new equation that will model angular velocity. And as we move through, we perform the differentiation again to generate a new equation for angular acceleration. Note that the angular acceleration equation has the form of a line, which is y equals mx plus b, where m is the slope, indicated by the negative 1106.58, and the y-intercept, which is 597.36. We see that the angular velocity highest power is a square, which would make this entire function a parabolic type of function. Now, to move from position to velocity to acceleration, we started with the first polynomial, a third order polynomial function we defined a little bit earlier, where A, B, C, and D are the coefficients, and theta prime is the angular velocity derived from theta. So angular velocity symbol equals the theta prime symbol, which is what we call the first time derivative of theta. And so to move from position to velocity to acceleration, the exponent decreases by a value of 1, and the exponent value is moved to in front of the coefficient and is multiplied by that coefficient. So 3 times negative 184.43 is negative 553.29, and the 3 becomes a 2. And then that process is repeated to generate the angular acceleration function. Individual coefficients without an independent variable are eliminated. So you can see the 0 reflects the fact that 92.2 is no longer a part of the function. So if we take those basic functions and use those to compute the kinematics of the foot, we would generate a number of patterns that would adequately reflect what's happening to the distal end of the segment. So when we talk about foot kinematics, these are linear kinematics. Recall that the angular kinematics reflected the movement pattern about the rotating segment. But now we concern ourselves with the linear pattern, rather the curvilinear pattern of the foot. So we start with linear velocity, which is the only velocity value for the foot, and it's tangential. And then from that we derive tangential acceleration, centripetal acceleration, the resultant acceleration, and the angle of that resultant acceleration vector. So we start with the linear velocity of the foot, which is the tangential, and we have the equation established earlier in which the velocity of the foot is going to be a function of the angular velocity and the length of that lower leg and foot, which we take to be 0.42 meters. And on this graph, what we see here, okay, and so this is the r is going to be a constant, and on the graph we see that the peak velocity of the foot aligns quite well with the angular velocity of the rotating segment of the knee here. So because r is a constant, omega is constantly changing and had that parabolic type of shape to it. And so we see the linear velocity of the foot following the same pattern. In terms of the acceleration of the foot, we start with the tangential acceleration defined by the equation r times alpha. Once again, r is a constant here, and to remind us of what the tangential acceleration vector looks like on this picture on the right hand side, here we see the foot following that circular pattern, and the tangential acceleration vector is directed at a tangent to that path, and so it's a direction that's constantly changing. The value also constantly changes. But because the r here is a constant, and our previous analysis showed that alpha is constantly changing, we see that the tangential acceleration follows the same pattern that we observed for angular acceleration, where we have a positive acceleration of the foot. That foot's acceleration moves through a zero acceleration en route to changing its direction into a negative acceleration. So the foot is accelerating in the downward direction past the 0 point, but even though it's accelerating downward, it has to overcome all of the positive momentum initially generated. And recall that the alpha equation previously is the equation of a straight line, and the slope is a negative, indicating that inverse type of pattern. So it's a linear function with a negative slope. Now, when we examine centripetal acceleration, recall this is the acceleration of the foot. It's a linear measure that reflects the tendency of the foot to accelerate towards the knee. Now, we know that the foot doesn't actually move towards the knee, but this acceleration counteracts the tendency of the foot to accelerate away. So let me get my mouse here, away from the lower leg. So they balance each other. And this is going to be a function of the angular velocity. Once again, r is going to be a constant here, but the centripetal acceleration being a function of the angular velocity of the knee or the linear velocity of the foot. These two equations can be used interchangeably. We see that the centripetal acceleration, the forces imposed on the foot, are going to be greatest at the mid-range point in motion. And contrast this with the previous slide, where the mid-range of motion saw a tangential acceleration of 0. So we calculate the resultant acceleration, which is the vector sum of the tangential acceleration of the foot and the centripetal acceleration of the foot. We see that throughout the entire motion, the acceleration of the foot is positive, but is least in the mid-range of motion. And so the unique pattern that is generated here is that we have the lowest resultant acceleration value at the midpoint, and it's quite flattened out. It's not quite that sharper parabolic shape that we saw a little bit earlier. Now, in terms of the acceleration angle, recall that this is the angle of the resultant acceleration vector from the rotating lower limb, so from the shaft of the lower leg. And what's notable here is that acceleration angle is 0 at the mid-range of motion. So what does a 0 angle mean? It basically tells us that with an acceleration angle of 0, the resultant acceleration vector is perfectly aligned with the rotating segment, meaning that the tangential acceleration vector is 0, and the only acceleration vector that is present is the centripetal acceleration value. And recall that the centripetal acceleration value is a function of the velocity of the rotating segment. And so we see that the acceleration angle is greatest at the very beginning and is most negative at the very end, reflecting the fact that the foot and leg are moving from a state of rest into into a larger velocity value. The velocity values decrease down to a 0 value, supporting the most negative acceleration values. So this ends this portion of our kinematics unit relating to the patterns in not just the angular kinematics, but the linear kinematics of the distal segment.